Hello, this is your astronomer from Helsinki. God, thank you so much for um, this time, giving this time to work on my project and to the ability to open it to the public via internet. So this is just me as a scientist working real time, and I have been actually struggling um, to organize it a lot. I feel like it's gonna take too much time to organize a coherent 1 hour video. So I'm gonna stop doing it because this is how a real scientist is working. Me, on a project, and it doesn't come on a platter to me. I do a little bit organization, so it's a little bit more digestible for videos and for the public. But so bear with me and keep it in mind. And I do work from home, so my husband is around doing something, so there's could be some noise. But we go forward, you know. So I was also thinking to write kind of with you the tutorial, write live the tutorial more than pre-write it and then execute it. So um, and I forgot to also say that let me stop sharing for a moment. Um, that all around me are also this is also an opportunity for me to bring more organization to the next level. I haven't gotten a postdoc yet, but I am kind of preparing in faith for a postdoc move. So I have recently graduated from the PhD degree, and there were many papers, um, you know, published, many projects, courses, and several projects had many publications associated with them. So I have like a lot of paper to deal with, and I assume when I move, I have to reduce. So I'm trying to digitize a lot of it and also to summarize my procedures better. It's an opportunity specifically for this type of project to summarize procedures, to write them better, and maybe, make shareable, more up to date um, online products for people. I don't know if it's going to happen, beyond this open science live stream, so to speak. Yeah, so I have a lot of papers and notes that I'm going through and revising, and um, I'm also trying to think how to some interesting ways to explain, because like you see, there's a lot of happening in spectroscopy. You have telescope observations, you have the science questions to deal with, the instrument specification, the IRAF or whatever programming language you use, and also recording and documenting everything you do. It can be uh, I forgot the it can be confusing, if somebody's watching, which is okay. It can be confusing. I lost my thought there. Maybe it will come back to me. Uh, yeah. Anyway, I constantly think how to improve. Maybe I'll teach a class one day or lead spectroscopy observations for young children. like high school children or undergraduates, if I have some teaching duties, for example, or if I work at a telescope and I need to explain. So it is also an opportunity for me to kind of learn to organize a science project into a digestible project. Right now, I'm doing as I'm doing. Of course, I have certain background in my mind and already. So I'm able to do this work. Maybe you have to look up some things that you don't know. I had to look up. I did my master's in physics. I didn't do a master's in astronomy. So the core of the courses was in physics. And I did um, all my teaching in physics before coming to PhD. So in a way, I had some catch up to do because some of the people in my PhD cohort they did masters or undergrad. All of their past was in astronomy, so they have done already observations. It was more familiar. And our program also has both bachelor's, I believe, and master's of astronomy. So in my classrooms also were dominated by people who did a lot of astronomy already. So I had to catch up. And even if you don't catch, you don't have to do that, and you do have a master's degree. When you do a project, you might have to look up something to learn. So I try to keep that in the back of my mind and put links and resources that if you need to look up something, like you identify you don't know what is bias or you don't know what is signal processing or something like that, then you can go look and read more if I give you the links. Yeah. So first of all, let's share again. Let's go. Let's open a new window. And am I sharing? Yes, I'm sharing. Astronomygo.com. Yes. Let's go to the tutorial where I am posting this. So here are the summaries of the tutorial. And in each video tutorial section or part, I give the title and the YouTube video link, as well as a link to the video tutorial notes. I write some highlight some important aspects of it, and then I started to also, in case you are um, doing job applications or learning to see, what skills and tools are used in that tutorial, and for more resources, I put different various links for to links and or papers or whatnot, including my own little how-tos. Um, Actually, I'm trying to learn to use GitHub and put my code on GitHub for public. So that's a new arena for me. So we'll see. We'll see. This is what I'm doing now. And I can now write, right, what did we do? Tutorial website. This is what we did. The link. So I guess we can do ADS next. So I'm gonna stop just to prepare my screen for it. Okay, so now the next resource indispensable resource for astronomers is the ADS, the Astrophysics Data System, where you can look up publications and get your citations. So it's ADS. Okay, ABS. It's a long, long, long link, but you can do. It's so important that it's. I believe, yeah, it's on my Google webpage, so you can just put it there and have it at your hand. Um, do I have it in my working? No, I don't. So in the ADS, in the modern form, which I use, what's a paper form? I've never heard of it. In the modern form, you can search. Usually, I search by author, but if I'm doing a larger literature search, a more broader literature search on a topic, let's say for that I'm not familiar with, then I would do a keyword search in an abstract or something like that, just to learn. Let's say when I was doing my thesis introduction to get the most up-to-date information, because I'm very intimately familiar with active galaxies field, but I know kind of the papers, the years, but the author names, but I'm not familiar, let's say CMB, even though it's very important, like dark energy. I don't know the most current papers or what's going on there because it's kind of textbook knowledge from my PhD. So when I was writing, I would read to learn what has happened between the last 5 years, last decade, on those topics that were in my thesis. Okay, but let's say, for example, for first author, we can do the obscured AGN. The last, yeah, it's Hickox. It was the first author of Astronomy Review on Obscured AGN in 2018. I could put here also end year 2018. And here is the obscured active AGN, and the data that I have collected is for obscured AGN environments. And then you can, for most a year or older publications, you can access their the full article, or you can often access for newer publications the archive article, or probably through your institutional access you have access to newly published articles as well. But let's say you don't remember the year, because I know it's a very important publication written by this author. I learned this trick from here. You can, restrict by year. I learned this next trick from my supervisor during my short-term research experience at ESO in Garching, from Dr. Michele Ginolfi. So he did my citation count. I overlooked what he was doing, and the most important papers usually have a lot of citations, so you can see right away. And there's another one that has more citations, but probably because it's been so also old. Sorry, I don't want to say the word old, but it's been published a decade before the 2018 paper. And the 2018 paper has 367 citations. You can now, let's use this. You can use this to find papers. For example, I was looking for IRAF papers, IRAF related papers, and I did title IRAF. That's how I looked for them. And you can also save the papers that you need into a personal library. You open your account and then click on the papers that you want. and go add papers to the library. I have a library for each project that I work on. I had a library for my own publications that have my publications, and I have a library like to read, papers that I'd like to read, library for my thesis. So I have, let's say, obscured AGN is for this project. Okay, obscured AGN, and then add, and one new record were added to library obscured AGN. Let me just check. Okay, is it making sense? All right, let's now come here, and some IRF spectroscopy papers are also important here. 1992 IRF spectroscopy reduction packages by Mr. Valdez, the XCCO. You can use this one as well. BCD reduction, long slit spectrum with IRF. So I add these IRF manuals into also obscured AGN library. Okay, 3 new records because several of them already existed. But I will add these to the resources file. So one of them, this, okay, so this is my obscured AGN library, and it has many publications in there, 22. I guess it's not that many. And one of them is, let me show you. I believe it was a long slit spectrum with IRA by Francisco Valdez. Is it? Here, you can have the title. You can check the affiliations, the authors, the abstract, publication information, keywords, and another, yes, you can see who cited. Usually you can see the references that say, citations that say used within that paper, but this is an older paper, 1986, so they didn't have, that's not listed here. Usually you can see graphics, which is cool when you need to borrow graphics here from the obscured AGN review. Something is not working, but usually you can see the graphics. And then you can export citation. You can copy to clipboard the citation and then go into your, for example, beep desk. See, how we can use this. This is my kind of mega beep desk file of all the references.bib that I use and have used in my publications. Almost all of them are there. And then you Control V, put it in there, reduction of long slit spectra, and you can give it a little code for retrieval later. Okay, and then save it. So you can use the citations to help you manage your references and transfers them into your references.bib file or whatever citation software you are using. And they have many different formats, like the MNRAS format. Yeah, okay. You can also have a custom format. All right, so if you are new to astronomy, you can create astronomy library of your interest. Is it transients or supermassive black holes, and put in the papers you like into that library. So now I'm gonna quickly write down what we've done in our tutorial. researched for IRF documentation, and learned about making an ADS library for the project. Yeah, I didn't show you how to make it, but you can just add a new library. When you add paper to library, you can create a new library here. So now I'm going to stop recording and clean my screen and write into the resources area the links to the IRAF documentation as external resources. All right, so the next step, I updated what we have done. We covered ADS libraries and including the BibDesk citation organization tool. Maybe I should put it here too, BibDesk tool. Now, the next topic to cover to understand what is going on, and it is good review for me too, is let's start, what is exactly these instruments that we are? What type of instrument is this ALPHOS? It's good to go read about it a little bit. It's actually kind of in a one of the series of this kind of instruments, ALPHOS, built by engineers, or I don't know who builds instruments, astronomers and engineers. Correct me if I'm wrong, but it is a CCT-based instrument. So let's start from the ALPHOS instrument page. It is the Alhambra Faint Object Spectrograph and Camera. Right? And if you go to here's the readout times, but we talked about it last time, if you go to the detector, what is this detector device? It's a CCD, blah, 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 some ID of the CD. Back illuminated deep depletion, Astra multi-tool. I don't know what those means actually, but it's a charged couple device, CCD. And before CCDs were able to take up pictures for astronomy, people used other types of instruments, like for example, photographic plates. So if you don't know what an astronomical term is, you can, of course, open a website on Wikipedia and read there with a grain of salt. There is a very nice Australian online database of knowledge for beginning and intermediate astronomy, I would say. But I looked up under C, there's no CCD. It's too technical, a little bit more advanced. But for example, there's a CMB and they have nice graphics and the language is accessible. So Cosmos, and I will put, it's an encyclopedia of astronomy. I will put it into resources somewhere. Maybe to just for the tutorial, two resources here. Resources, Cosmos, online database of, I guess, online encyclopedia. By the way, I use Dvorak to type, blind typing. Okay, it was not there. Well, I used a book to learn about CCDs by Steve Howell from University of Arizona. It's called Handbook of CCD Astronomy, and those explanations made sense to me. When I believe my master's supervisor let me borrow his book because but if you don't have the book, you can go to the library. I not a student. I have never been a student of University of Helsinki, but I live in Helsinki. And there are two big universities, Aalto University and University of Helsinki, and maybe more universities, which I'm not familiar with very well. But those universities have some astronomical studies going on. And I have registered with both libraries, and they allowed me to use those libraries. So um, I found that in the University of Helsinki library, there are a lot more physical astronomy books. So uh, I searched for CCD Astronomy on the library website, and I saw if I need a refresher from Handbook of CCD Astronomy, I can borrow it. They're all read online, so you can read online. I'm not sure if I can read it if I'm not a university student. We'll see. But another book that I caught my eye was A Practical Guide to CCD Astronomer by Patrick Martinez and other people. Um, it is also available online. So you can use your library. The city library doesn't have these texts. So I needed to go to a university library. Um, yes, so let's put that. I'm gonna stop my video and put these titles into the um, video tutorial file records. All right, so I updated the resources, and I forgot to tell you that this a reference file from BibDesk you can use to add references and citations and bibliography part of your in the manuscript. Um, so in this manuscript that I'm writing, let me update it so it's not dormant. They have instructions on what to do. So I have to use these commands, and my file is references. I drop it here, upload, and then we can begin. Is it like this? Let's see. It's a new template for me because I never use AA template. No, I have two references for some reason. Maybe don't need this. Okay, references. Now I can use references here. And the way I would do it is to, let's say, if in the introduction I introduce obscured quasars represent the dominant population of quasars. For example, AGN, obscured quasars, or type 2 AGN, or the population of AGN. And I can cite here this. So the citation comes here in text, and then the citation appears in references as well, the full reference to it. And another example could be type 1 aging environments have been investigated through spectroscopy previously in gamma spectroscopic survey. Um, Type 82. Okay, maybe I can do more general previously. And I can do even more papers in one citation. I think it was 2017. Yeah, and all of them appear here and all of them appear in text. So this is the beauty of using these organizational tools for your for managing your bibliography. Okay, so now back to our tutorial. Um, in our steps previously, we downloaded the data, we focused on observations from one night and sifted through the files of that night, and we combined in IRAF combined routine 3 science images to get rid of cosmic ray hits for one quasar. We are focusing on this quasar 103. And let's remember what it is actually. For that, let's so quasar 103, this is my observing proposal, has these coordinates. It has this brightness and its redshift is 0.2064. So let's write it actually into the research notes. Deck R. To bring it to kind of more tangible of what it is. Now we can use a sky view tool such as SDSS navigate tool. Okay, try a new version. Here it is. We will need our coordinates. Array, these are SDSS based quasars, so they are in the SDSS footprint. Here is this navigate tool. It shows you the sky, images of the sky in certain bands. Here you can put, have some searching parameters such as array and deck. And I input them. I haven't used the DR18 that much, but here you go. I updated it. And now we can use a grid. We can Look at photometric objects and objects with spectra, something like that, right? I don't know. They are 18. Maybe is there something about coordinates? Let's do, or is it not accepting? It needs decrease. Is that what it is? Or did I forget the plus sign? This is a little bit older version of the navigate. We can put a grid. We can also put the objects with spectra, and here it is identified. So I don't know, maybe I made a mistake with the R18. Let's invert the image. But this is the quasar. When you have when you click objects with spectra in red squares, the navigate tool shows you those objects for which it has spectra. So if I zoom out, I must see more objects with spectra. So you can see that the images and photometric objects identified by SDSS in blue circles are quite many. However, the spectra has been collected only for few spectra have been collected only for a few objects, including quasars. I am really surprised that DR18 didn't work because it looks better. Way. Let's try new version. Show objects, but okay, here you put your coordinates. Or no. It's not working. Okay, can we go to old version? Fine. Ah, there's nothing. I don't know. If you know, please put in comments. Tell me what am I doing wrong. But it's not minus, it's plus. Is it not liking the array in deck? Is it not converting correctly? It's doing something weird. Okay, we'll give up here. We can, you know what we can do for quickness? You can calculate array and deck in decrease, or we can, now that this is here, I can click explore. And by the way, here's the mini spectrum. If you click on it, it shows that it's a QSO broadline AGN. Okay. Here I have the coordinates in decimal. Decimal, which we can put into here, and it must work. In the previous version, it converts correctly. Okay, fingers crossed. Looks like we found our object. Okay, so there is something wrong with the orange deck. I guess it's written here degrees. In the previous data release, it would convert automatically. We can, zoom in on the object, but this is our quasar. This is an obscured quasar we are investigating. Um, okay, and then we can click objects with spectra. So here's a red square showing that there is a spectrum for this object. Let's see, for example, this galaxy is 0.207. Look, it's close in redshift, so later we have to explore it. We have to explore all the available spectra. The spectra that by the time we write our results that we have collected and the spectra that exist in archives, we'll have to go and make sure we have all the available spectra from the archive as well to add into the paper. Um, so yeah, you can explore this object. It gives you a bunch of information from different surface cross identifications, any other observational information, the magnitudes, errors, redshift. This is so new for me. I don't know where to look because I haven't used this updated version. Where's the photo Z, but where's the real Z? The spectroscopic Z. I don't know. Optical spectra here. Here's a spectroscopic Z, 0.207. Here is identified as a galaxy. It's an extended object. I'm looking at a different. Let's go back to our quasar. Explore. Yeah, this is our quasar. Doesn't it look like there's two nuclei? I don't know. I don't know. But there are a lot of, objects nearby. Are they projection effect or some of them are real galaxies close to that quasar? I don't know. Very interesting. It's always so fun to look um, at at the sky for me. Here's the optical spectra, and let's see. Here's the interactive spectrum. You can. Oh, there's another error. I guess they're working on this. Analyze spectrum. What is? Anyway, let's go to the older version. The interactive spectrum. It's also not working. SDSS. Come on. Actually, an important another important place to look up objects that are galactic is a NED net um, extragalactic database. And here we can input our coordinates. It's my husband saying that they're almost here. Okay. Yeah. Just really quickly, you input your coordinates, you click go. And here you can see information about that object. See, it has been observed just by the names, the SDSS, and maybe a WISE QSO, right? And you can click on each. So I haven't used that much this new one. Let's see. These are object type, blah, blah. If you click on object type, let's see the WISE one because it's labeled as QSO. gonna do. It's so slow today. Mhm. Different. Um, yeah, these are different objects, and you have to be careful. It's not the same object necessarily that you put in. These are different coordinates, which are further and further from the coordinate that you in did input. Here it shows you the separation. Uh, it shows you what photometry there is. So the one I clicked, it has 64 photometry observations. Um, let's see if it opened. Great. So no, I'm very familiar with this. So you have cross IDs, coordinates, redshifts, all of this information, spectra, references, what papers reference this particular object. Um, the SED is always fun to look at. Look, it has been observed in the UV, SDSS optical, GRIC bands. Looks like there is two mass observations in infrared WISE survey. It's also a WISE object. So there you go. Here's the SED, the spectral energy distribution. Isn't it exciting? So this is the um, navigate uh, based image. Where is our image? So when I look at the acquisition image in our observations, which so here is a spectrum. I marked it with a green. Right before the spectrum, we take acquisition image. It's the image of the field. It is not very deep image because it was very fast. Now hold on, this is helium neon. Okay. It's a helium neon image. This is a slit image. Okay, let's start from the beginning. This is a acquisition image. Um, this is the same image as here. The same patch of sky. You can use actually stars. You can use stars to orient. The dimensions are not the same because this is a larger, but here is my that should be in the center. So probably this little guy is this guy. Is it right? Is this our object? So Chamberlain, yeah. Okay. Is it just double check, make sure I'm looking at the correct. No, this is not ours. Let's go back and find again our object. Make sure we're looking at the same object. How did we do it? We used a different. So let's think. Maybe if we invert. There are two big stars. Maybe it's these two big stars. There's these three. Could it be these three stars? Yeah, this. Them. Okay, yeah, because actually I see what is my mistake. Um, Even though we're observing a QSO 103 field, QSO 103, I labeled it, it's actually the spectrum is the slit was actually the purpose was to observe the neighbor around the quasar. So this is my neighbor. I need to know it doesn't have the spectra from SDSS database or any other database. So I collected spectrum of this uh, bright neighboring galaxy. So if I actually click on this, bring it kind of to the center. So this is my galaxy, the neighboring galaxy to this obscured quasar for which I collected the spectrum. And it's this central object here. This is the quasar. So we can then, label it. This is quasar. Quasar. We will call it galaxy A. Maybe let's make it bigger. It's QSO 103. This is galaxy A, which is close to this quasar. So these are kind of my three guiding stars to make sure that the sky is oriented the same way. Um, these are these two other bright. I'm not sure if they are stars or maybe stars, or I think they're stars. Two other bright objects here. So I'm in the same correct space. Um, what did I want to say? So yes, this was the acquisition image of the whole field centered on this galaxy, which is a neighboring galaxy to my obscured quasar. This is an object, the galaxy is a neighboring galaxy to the quasar for which we are studying and trying to identify its scientifically meaningful spectrum with IRAF and with other tools. So that, and then what happens, you put um, let's I have no. So this is my slit now. And I will show you, because then when you put the slit, you cover everything else and you focus on this object. Let's actually give me a little bit of space. You focus on this object. And it's a galaxy, so it is possible if your slit is not wide enough that you lose signal. So no, but your signal. Okay, can I draw better? We can do it. We can do it. Pretend it's symmetrical, more or less. I want this. So what do I mean? Um, there is more dark here, so you get a higher signal, but the galaxy uh, pixels or the parts, the galaxy is an extended object. It might be extended beyond this slit, so you lose in a way some information, but that's we will account for it later in a step in one of the final steps. But the slit allows you to focus on this object. So in our acquisition images with Alphosk, then here is when you put the slit there, here's the image. However, what did I do? I didn't put slit like this because I also wanted to obtain slit um, spectra from the quasar off center. So I can't rotate it uh, in this software, but I put the slit like this at an angle. And this is the positional angle we are talking about. Over A. Okay. To collect off-center quasar spectrum. So we should see at least two spectra, two dispersed spectra in our data. So here you go. Or maybe I collected some extra spectra. I have to double check my notes. I'm just talking out of memory right now. But here you can see in the center, actually I can guess that, can I go Control Z, Control Z? Okay. Actually, in this particular case, I can see that this is my object from the this white light here. Can you see it? This white signal here. This is my galaxy A. And then there are two more spectra. I'm pretty sure these are these two spectra. So even though I have one long slit, I tried to collect more than one spectra, but it is very difficult to collect more than one spectra because what's the optimal position for one might not be optimal position for a second one. Anyway, I always had to make sure that this one in a center is the main target object is observed well, and if possible, observe other two. But this is quite bright, but it might be a star. And here's another one. So there are at least three spectra. So this is now an image of the field, but with a slit. So everything else you don't see here. You only see this little strip. And when you have a slit, light, a source of light going through a slit, it behaves. It creates rainbows. So when I go and uh, open my file, so this slit image basically is repeated here over and over and over and over and over again in different wavelengths. it creates a rainbow. Red wavelengths on the bottom and bluer ones on the top. Unfortunately, it's less the moment go. Unfortunately, so this is a central. But I was saying that unfortunately, towards the bluer wavelengths, the signal is worse. You can see here. This is one of the exposures. You can have this central spectrum of my object, my target object, and few more. Here's some other faint spectrum, probably cut there by chance. So I have 1, 2, 3, 4, 5. Can I count spectra? 1, 2, 3, maybe 4 have good signal. I'm not sure about this one. A lot of cosmic ray hits. Now we use so this is your spatial axis. See, I identify that this is in the center. This object is in the center of the slit. And this spectrum is in the center of the slit. So each vertical row or something, band, I said it wrong. Each horizontal band represents an image of this slit in different wavelengths. It's like a rainbow. If you had a color, can we color it? What is it called? Sorry. Well, um, it's not realistic. Each horizontal band, these bright lines are skylines, unfortunately. They mess up my observations. But this space between these two spectra, between these two vertical bright line, each vertical bright line is a spectrum signal. This space is empty space. I guess it's this space here. And you can see that the width actually of the acquisition image is right here. The field is larger for the covered by the field covered by the slit is larger than the acquisition image of the slit. What else? Okay, now this is the bad kind of the single exposure. It has all these cosmic ray hits, but it comes out better when you use, as we did with ion combined, we used signal processing method. Of the um, signal to noise improvement and combined made a average of 3 exposures, which improved the quality of the signal to a certain extent. And in particular, these bright spots, which are cosmic ray hits, and are removed because, let me just delete, close all of this, because cosmic ray hits are random and every time they hit in different positions. So when you do the average, you get a better, cleaner spectrum from these 3. Okay, I'm gonna stop here. And because I have to, we didn't do anything with IRAF, but I feel like I have to explain a little bit. So it's not like I'm typing some commands, something is happening. So let's bring in some visuals to understand what's going on. But now maybe you can relate a bit more and I can relate and admire and marvel on our beautiful cosmos that we had taken spectra of this object, maybe these objects, with our long slit. And now with IRAF tool, we are able to analyze the rainbows of these marvelous celestial objects, including a galaxy next to an obscured galaxy, and answer some, hopefully, scientific questions, such as measure its distances through redshift, which you can do by using spectrum, measure its star formation rate estimate if there is a O2 emission line. Right now, I don't see any prominent emission lines visible here. So we'll see. Maybe it's an old galaxy. I wonder what is the UGR. I see. Okay. All right, I stop here. Um, I will quickly write what these tools and put it in video tutorial, and we continue next time. Isn't it exciting? God bless.